In a distant corner of the universe lies NGC 1277, a colossal black hole so ancient it seems frozen in time. How did it stop growing while the cosmos kept evolving? Tonight we'll uncover one of the strangest relics ever found. If you enjoy exploring the mysteries of space, please like, subscribe and share, and tell us in the comments, do you think time can truly stand still in the universe? Thank you for watching. Now let's begin. Across the vast reach of intergalactic space, the Perseus cluster stands as one of the nearest and most studied collections of galaxies in the known universe. It lies hundreds of millions of light-years from the Milky Way, a colossal gathering bound by gravity and enclosed within a vast halo of hot gas. Observed in X-rays, the cluster glows with diffuse light emitted by plasma heated to tens of millions of degrees Celsius. The luminous fog stretches across millions of light-years, filling the region between galaxies with an invisible pressure that sculpts their motion and evolution. Within this sprawling web of gravity, hundreds of galaxies orbit a common center of mass, each one tracing paths that have persisted for billions of years. At the heart of the cluster lies NGC 1275, an active and complex galaxy powered by a supermassive black hole that floods the surrounding space with jets of high-energy particles. Around it, in quieter orbits, smaller systems drift in slow arcs through the gravitational basin of the cluster. Among them is one galaxy that appears unusually calm, compact, and old, NGC 1277. The Perseus cluster itself is a dynamic laboratory of cosmic history. Its galaxies vary in form and age, from spirals rich in dust and star formation to ellipticals long faded to red. The hot intracluster medium acts as both connective tissue and sculptor, stripping gas from galaxies that plunge through it at thousands of kilometers per second. As these galaxies move through the medium ram, pressure removes the cold hydrogen that would otherwise condense into new stars, gradually shutting down their growth. Over time, the most active spirals transform into featureless lenticulars, their disks smoothed and star formation quenched. This slow environmental shaping defines the broader context in which NGC 1277 has existed for eons. Yet the small lenticular stands apart. It does not simply appear as a quenched descendant of a spiral. Instead, its characteristics suggest it has been fundamentally unchanged since the early universe, as though time halted shortly after its birth. Seen through optical telescopes, the Perseus cluster forms a rich tapestry of light. In wide-field images, its member galaxies glimmer like isolated islands within a faint sea of intracluster haze. Faint trails of starlight mark the gravitational tides between them. Thin streams formed when stars are pulled away during close encounters. Gravitational interactions are frequent here. The cluster's deep potential well pulls smaller members into complex orbits, where they occasionally brush past one another or through the extended halo of the central giant. Yet despite this bustling environment, the small lenticular known as NGC 1277 retains a remarkably undisturbed structure. Its outline is smooth, its stellar light tightly confined, and its profile largely unchanged for billions of years. To locate it within the cluster is to find a remnant of an earlier cosmic era, a fossilized form surviving amid continual change. From a distance, the Perseus cluster reveals a hierarchy of scales. The dominant gravitational mass is carried not by the visible galaxies, but by the invisible component of dark matter, forming a cluster-scale halo that holds the system together. Superimposed upon this deep gravitational potential is the hot gas that emits the X-ray light seen by telescopes such as Chandra and XMM Newton. This gas is tenuous, only a few particles per cubic meter, but so vast that it outweighs the stars themselves. Through this medium, sound waves ripple generated by the activity of central black holes that pump energy into their surroundings. These pressure waves have been mapped by astronomers as patterns in the X-ray glow, resembling ripples in water spread across intergalactic distances. Within these conditions, galaxies like NGC 1277 move as small self-contained systems embedded in a much larger ocean of matter and energy. Each orbit within the cluster is influenced by both gravity and resistance. While gravity keeps galaxies bound, the hot intracluster medium exerts drag, slowing their motion and removing gas. The process is gradual but inexorable, stripping away the raw material required for star formation. Over many billions of years, galaxies lose their outer envelopes of gas, becoming inert collections of aging stars. NGC 1277 fits naturally into this landscape of stripped quiescent galaxies, yet its properties suggest that even before the cluster's environment began to shape it, this system was already different, denser, older, and more compact than its neighbours. Its stars formed quickly in the early universe, exhausting the available gas in a cosmic instant, after which the galaxy simply aged in place. It became a time capsule from the era when the first massive galaxies assembled, preserving conditions that elsewhere were erased by later mergers and growth. To understand its context, one must picture the Perseus cluster not as a static grouping, but as a constantly shifting ecosystem. The central galaxy NGC 1275 anchors the cluster's gravitational well and dominates its visible light, while hundreds of lesser members orbit in elongated trajectories around it. Many of these galaxies bear scars of encounters, warped halos, extended tidal tails, and disrupted star streams. NGC 1277 shows none of these signs. It is remarkably compact, with a half-light radius of only a few thousand light-years, far smaller than the Milky Way. Its total stellar mass is measured in the hundreds of billions of solar masses concentrated into a dense spheroid that spins rapidly around its axis. Such structure indicates a formation event in which nearly all of its stars were created within a very short time, perhaps less than a billion years long, before the Perseus cluster itself fully assembled. In the broader picture, the cluster acts as an archive of galactic evolution. Some of its members continue to interact, merging and growing as gas funnels inward to trigger new bursts of star formation. Others, long deprived of fuel, fade into dormancy. Among them, NGC 1277 represents an end state reached early and maintained ever since. It orbits near the core of the cluster, bathed in the soft X-ray light of the surrounding gas, yet its internal composition and structure have changed little since its formation. Observations from the Hubble Space Telescope and the Keck Observatory reveal a smooth, featureless disk of old reddish stars with no visible dust lanes or star-forming regions. This lack of disturbance implies not merely quenching, but true stasis, a galaxy that has remained dynamically quiet for over 10 billion years. Within this section of the universe, distances are immense, but gravitational ties are strong. Each galaxy within the Perseus cluster feels the collective pull of the whole orbiting a center that shifts subtly as mass redistributes. NGC 1277's motion through this environment is measured through its redshift, corresponding to a velocity of thousands of kilometers per second relative to Earth. Yet on the cluster scale, such speed is modest. Over billions of years, its path traces a gentle ellipse within the dense core, returning again and again to the same region of space. The stability of this orbit may have contributed to its preservation. Unlike galaxies that venture to the outskirts and fall back inward through the hot medium, NGC 1277 remains near the center, where gravitational tides are strong but encounters rare. it has likely avoided the kind of disruptive collisions that would have stirred or expanded its structure. The Perseus cluster continues to evolve even as its individual members age. The central gas slowly cools, leading to new inflows toward the largest black holes. Radio jets extend from the cluster's heart, depositing energy back into the medium and preventing catastrophic collapse. Yet amid this cycle of activity and feedback, NGC 1277 endures as an exception. It neither feeds nor is fed. Its stars have long since burned down to slow, steady phases of fusion. Its interstellar medium is thin, devoid of cold molecular clouds. Its internal light, seen from space telescopes, carries the spectrum of ancient metal-rich stars, evidence of a past so intense that it exhausted itself. To study it is to glimpse what galaxies once were before mergers and accretion reshaped the universe's great structures. In the quiet depths of the Perseus cluster, surrounded by plasma gravity and faint starlight, this small lenticular drifts unchanged. It is one among many, yet unlike any of them in its stillness. NGC 1277 remains as a cosmic relic, frozen not in temperature but in evolution, a survivor from a time when galaxies formed quickly and ceased just as swiftly. The environment around it continues to glow, move and transform, but the relic itself remains locked in an ancient equilibrium awaiting closer study. NGC 1277 moves within the restless depths of the Perseus cluster, surrounded by the diffuse glow of intergalactic gas that hums with quiet energy. In the broader view, this region is defined by its X-ray brilliance, an immense field of hot plasma, emitting light invisible to the human eye. The intracluster medium fills the space between galaxies, reaching temperatures of tens of millions of degrees Celsius and shaping their evolution through slow but unrelenting pressure. It is a landscape without air yet rich in motion, where gravity and heat are the only sculptors. The Perseus cluster stands as one of the largest gravitationally bound systems in the local universe, and its activity echoes across millions of light-years. The luminous fog of ionized gas acts as a silent sea dense enough to slow galaxies that pass through it. Embedded within this cosmic ocean, the compact Relic galaxy maintains a steady orbit near the cluster's heart, immersed in an environment that would strip any ordinary system bare of gas and dust. Yet the lenticular fossil already surrendered its fuel long before the cluster reached maturity. The light emitted by the cluster's hot plasma is observed through telescopes tuned to high-energy wavelengths. The Chandra X-ray Observatory and the XMM Newton mission have mapped intricate ripples and cavities in this glow, signatures of pressure waves moving through the gas. These waves, generated by the activity of central black holes, create vast concentric rings that trace energy feedback within the cluster. The central galaxy NGC 1275 releases powerful jets of charged particles that carve out depressions in the X-ray field. Around these structures, sound waves travel through the hot medium, each one spanning hundreds of thousands of light-years. Within this grand acoustic landscape, NGC 1277 remains silent, emitting no strong radio jets and showing no sign of recent accretion. It drifts like a fossil preserved in the heat, orbiting through the same environment that reshapes its neighbours. The contrast between the cluster's turbulence and the galaxy's stillness defines its peculiar nature. At optical wavelengths, the Perseus cluster offers a different view, a web of stellar systems woven into a faint background of scattered light. Astronomers studying this field observe how galaxies interact and evolve under the cluster's immense gravitational pull. Tidal forces stretch and shear them, while the intracluster medium erodes their cold gas reservoirs. The balance of gravity and resistance determines whether a galaxy can form new stars or whether it will fade into quiescence. For most, this process unfolds over billions of years. For the Relic, it ended abruptly and early. Long before the cluster's gaseous halo reached its current extent, the stars of NGC 1277 had already formed and aged. Its surface brightness remained steep, its light concentrated toward the center, revealing a dense stellar population that long ago exhausted its fuel. No extended halo of young stars surrounds it. No spiral arms or tidal tails betray recent interaction. It is as if the galaxy was completed in the universe's youth and has since remained untouched. The position of the Relic within the Perseus cluster's gravitational field is both stable and revealing. Located near the dense core, it experiences the constant influence of the cluster's collective mass, but avoids the violent interactions found at its turbulent edges. The cluster's central potential well is deep, and galaxies orbiting within it follow elongated paths periodically approaching the center, where gravitational tides are strongest. During each passage, those that still retain gas may experience bursts of compression that ignite short-lived episodes of star formation. The frozen remnant shows no such cycles. Its motion is steady, its light uniform, its spectrum consistent with stars older than 12 billion years. In this environment, dynamical friction and tidal stripping continually alter the fate of other systems, but the Relic endures without measurable change. Its small size and compact structure make it resistant to disruption, allowing it to survive unscathed where larger galaxies are gradually reshaped. The intracluster gas surrounding the galaxy plays a dual role, both destructive and protective. Its heat prevents the condensation of new gas within the Relic, ensuring that no further stars can form. Yet its pressure also cushions against smaller collisions, dispersing potential impactors and preserving the lenticular's compact core. This equilibrium allows NGC 1277 to remain intact as it navigates the dense center of the cluster. The galaxy's outer stars experience the faint drag of the medium, but their orbit is too tight, their cohesion too strong for the structure to unravel. Over cosmic timescales, this balance has left the galaxy's outer profile remarkably smooth. High-resolution imaging from the Hubble Space Telescope reveals no signs of ongoing star formation, no dust lanes, and no irregularities. The absence of cold gas is total. Even the faint infrared glow that would hint at residual star-forming activity is missing. The lenticular fossil appears not merely dormant, but utterly inert. Around it, the Perseus cluster remains a dynamic system. The gravitational potential of the entire structure is dominated by dark matter, which binds together the visible galaxies and the hot plasma that fills the spaces between them. The density of this invisible matter is mapped through gravitational lensing, small distortions in the apparent shapes of background galaxies. These distortions confirm the presence of mass far exceeding that of the luminous components. The Relic's motion, like that of every cluster member, is guided by this unseen scaffold. Despite this, the compact system exhibits little evidence of a dark matter halo of its own, a subject that continues to challenge astrophysical models. Whether this is an illusion caused by the stripping of its outer layers or a genuine absence remains an open question. From its place in the cluster core, the galaxy reflects both the history of early cosmic assembly and the complex interplay of forces that govern the evolution of massive systems today. Viewed through the combined lens of X-ray and optical data, the Perseus cluster reveals layers of structure and energy. Each galaxy within it contributes to a collective rhythm of motion and light. Some, like NGC 1275, remain active, feeding their central engines and stirring the surrounding gas. Others drift quietly, their stars aging and fading without renewal. The compact Relic belongs to this latter class, but distinguishes itself by degree. It is smaller, denser, and older than most. Its stellar population formed in a rapid burst when the universe was less than 2 billion years old. Its continued presence, largely unchanged, offers a window into a formative era of galaxy building. Through it, astronomers can study how early massive galaxies might have appeared before subsequent mergers and growth events reshaped them. In that sense, the Relic is both participant and witness, existing within the modern cluster while preserving the conditions of a distant epoch. As the Perseus cluster continues to radiate in high-energy light, the quiet lenticular remains as a contrast of permanence amid change. The hot gas bright in X-rays forms a turbulent sea where energy flows from active galaxies outward. Shock fronts ripple through the medium. Cavities open and close as black holes inject energy back into their surroundings. Against this background, NGC 1277 remains dim and stable, moving along its orbit as it has for billions of years. The cluster's light may fluctuate and its plasma may shift, but the Relic's internal structure endures unchanged. Its path through space traces a long ellipse that repeats endlessly, marked only by the slow drift of cosmic expansion. In this motionless persistence, the galaxy represents a kind of equilibrium rarely found in such crowded environments. While its neighbours evolve, collide and transform, the Relic continues unaltered, embodying the memory of the universe's earliest and most efficient era of star formation. NGC 1277 presents itself as a smooth, compact lens of ancient light within the crowded core of the Perseus cluster. Classified as a lenticular galaxy, it bridges the form between an elliptical and a spiral, retaining a disc-like outline yet devoid of spiral arms, dust lanes, or regions of active starbirth. Its surface brightness falls sharply from centre to edge, creating the impression of a galaxy, compressed by its own gravity. Through telescopes, the Relic appears featureless, glowing with the reddish hue of old stars. This subtle coloration is not a cosmetic trait, but a record of stellar age and metallicity, the chemical maturity of a system that formed quickly and then ceased. The lenticular fossil measures only a fraction of the Milky Way's diameter, yet it holds a stellar mass comparable to many much larger systems. The result is extraordinary density, a concentration of luminous matter packed tightly within a few thousand light years. In such a compact volume, the motions of countless stars overlap, creating a smooth, continuous field of light when seen from afar. Astronomers studying this ancient system often describe it as a relic from the early universe, a survivor from a population of compact galaxies that once dominated cosmic structure formation around 10 billion years ago. Observations from the Hubble Space Telescope and ground-based adaptive optics have confirmed its remarkable compactness. Whereas most galaxies of similar mass have since expanded through mergers and accretion, the Relic has not. Its stellar distribution remains confined to a central spheroid, wrapped by a faint, tightly bound disk. The light profile indicates a Cercic index typical of dense, early-type galaxies, signifying that most of its mass resides near the centre. These structural characteristics align with simulations of primordial galaxies, formed during the peak of cosmic star formation, when gas collapsed rapidly and efficiently into stars under the influence of immense pressure and gravity. In the modern universe, such galaxies are rare. Most have been reshaped into larger, more diffuse forms through countless mergers. The compact Relic galaxy's apparent stillness belies the complexity of its internal motion. Spectroscopic measurements reveal that it rotates rapidly with stellar velocities reaching several hundred kilometers per second. This rotation is not visible in its smooth appearance, but is embedded in the subtle Doppler shifts of its starlight. The pattern suggests a flattened system that retains some of the angular momentum of its original collapse. Yet the absence of spiral structure and the dominance of old stars confirm that the disk no longer forms new generations. The equilibrium between ordered rotation and random stellar motion defines its lenticular identity. Inside the core, velocity dispersion dominates, indicating that stars move in all directions under the strong gravitational pull of the central mass. This balance between rotation and pressure holds the compact relic together, maintaining its dense form without external support. The galaxy's flattened shape is thus a memory of its rapid birth, frozen before subsequent mergers could disturb its symmetry. The environment within the Perseus cluster reinforces this stability. Immersed in the hot, low-density gas of the intracluster medium, the relic experiences minimal external disturbance. Its lack of cold gas shields it from ram pressure effects that might otherwise strip or distort it. Meanwhile, its small cross-sectional area reduces the probability of direct collisions. Over cosmic time, these factors have allowed it to preserve its original configuration. This isolation contrasts with the fate of typical lenticulars, which often form through the transformation of spirals stripped of gas by their environment. The compact fossil appears instead to have been born as it is a product of early rapid formation, rather than late environmental quenching. Its dense, featureless disk represents a structure assembled under extreme conditions, then left to drift unchanged for billions of years. At optical and infrared wavelengths, the galaxy's light provides a precise chronicle of its age. The spectral absorption lines of magnesium and iron indicate a metal-rich population enriched by successive generations of short-lived massive stars. The abundance of alpha elements such as oxygen, magnesium, and silicon relative to iron suggests a formation timescale shorter than 1 billion years. In such a period, massive stars would have exploded as supernovae, enriching the surrounding gas before it condensed into lower-mass, longer-lived stars. The result is a uniformly old stellar population with high metallicity and little variation across the disk. This chemical uniformity reflects a burst-like formation history rather than gradual enrichment. Once that burst ended, star formation shut down almost entirely, leaving behind a population that has aged passively ever since. The reddish glow visible today is the cumulative light of these ancient cooling stars. Detailed measurements of its surface brightness profile reveal a small bulge-to-disk ratio, with the bulge dominating the inner region. The effective radius, the distance within which half of the galaxy's light resides, is roughly 1/6 that of the Milky Way. Within that small sphere, the stellar density rises steeply toward the core, reaching values that challenge conventional models of galaxy formation. Such compactness implies that the relic formed when the universe was denser overall, allowing matter to collapse into smaller, tightly bound configurations, before large-scale mergers inflated galactic sizes. Over the following billions of years, most galaxies of similar mass grew through collisions that added outer envelopes of stars, expanding their radii. The relic avoided this path entirely, keeping the proportions of an early universe galaxy within a modern epoch cluster. It is a rare physical link to the compact massive galaxies seen in deep field surveys of the young cosmos. The galaxy's structure also reflects the imprint of its dynamical history. Within its disk, stellar orbits maintain coherence, rotating in a plane aligned with the galaxy's minor axis. The stars in the bulge, by contrast, move in random orientations, producing a high central velocity dispersion. This configuration indicates that the system has long been dynamically relaxed, a state achieved only after billions of years of gravitational mixing. In such a stable configuration, no large-scale disturbances remain to stir the stars. Every orbit has been averaged over time, creating the smooth light gradient observed today. The absence of dust lanes or cold molecular gas confirms that the interstellar medium has been fully depleted or expelled. Without gas to absorb and scatter light, the stellar continuum appears unbroken, and the galaxy's spectral energy distribution remains sharply defined. The Relic's quiet rotation and compact structure thus preserve a state of equilibrium rarely seen in the nearby universe. Within the Perseus cluster, the compact Relic's motion is measured relative to the surrounding galaxies. It travels at thousands of kilometers per second with respect to the cluster center, but follows a stable path influenced by the collective gravity of the cluster's dark matter halo. The velocity dispersion of the cluster as a whole exceeds 1,000 kilometers per second, creating an environment of constant movement, yet internal collisions between galaxies are rare due to the vast distances separating them. In this vast but tenuous arena, the compact lenticular moves as a single body, its internal equilibrium unaffected by the larger flow. The contrast between the cluster's chaotic energy and the galaxy's serene self-containment is striking. One represents the collective turbulence of structure formation, the other its fossilized remnant. When viewed as part of the cluster's grand design, the Relic serves as a fixed reference point amid perpetual motion. While other galaxies merge, stretch, and ignite, this one endures as an unchanging beacon. Its light crosses the cluster's hot gas without distortion, carrying to observers on Earth the spectral imprint of an early epoch. Each photon that leaves its stars today has travelled for hundreds of millions of years, traversing intergalactic space before entering our telescopes. In those faint signals, scientists decode the story of a galaxy that formed fast-aged quietly and now exists as a living relic of cosmic dawn. In the stillness of its lenticular frame, the ancient system reveals the power of preservation across cosmic time, a rare survivor from an age when galaxies were young and the universe itself was only beginning to take form. NGC 1277 stands apart within the Perseus cluster, not only for its compact form but for the deeper implication that it has remained almost entirely untouched since the universe's early epochs. Astronomers often refer to it as a relic galaxy, a phrase that carries both scientific precision and a sense of quiet endurance. The term describes a system that appears to have stopped evolving after its initial formation, preserving the density and structure characteristic of galaxies seen when the universe was only a few billion years old. In the case of this compact lenticular, that preservation is nearly absolute. Its stars, all ancient and metal-rich, tell of a single rapid burst of creation. The resulting population forms a fossil record of a time when the cosmos was much denser and more turbulent than it is today. The absence of later mergers, gas inflows, or tidal distortions suggests that the galaxy entered a long period of dormancy soon after it formed, effectively freezing its evolution, while others continue to grow and change. To observe it now is to witness an object caught between epochs, ancient in substance, contemporary in location. In the early universe, galaxies were smaller, denser, and more compact than their present-day descendants. They formed through the rapid collapse of gas clouds within dark matter halos, leading to intense but short-lived episodes of star formation. These early systems, observed today only at great distances through deep field surveys, appear strikingly similar to the structure of NGC 1277. Their compactness, high stellar velocity dispersions, and reddish colours suggest that they too underwent early and efficient starbursts before fading into quiescence. Over the next 10 billion years, most of those primordial systems would grow, through mergers accumulating outer envelopes and transforming into the large elliptical galaxies that dominate clusters today. Yet the relic at the heart of Perseus never took that path. For reasons still under study, it avoided the merger-driven evolution that reshaped nearly every other galaxy of its class. This isolation has allowed it to survive as one of the closest known analogues to the compact massive galaxies of the young universe. The idea of a galaxy preserved in such a state challenges the expected flow of cosmic development. Models of galaxy evolution predict continual interaction, accretion, and structural growth. Within a dense cluster, collisions and mergers should be frequent over billions of years, steadily enlarging galactic envelopes and mixing stellar populations. NGC 1277 defies that expectation. Its smooth surface and uniform age distribution show no trace of secondary growth. The most plausible explanation is that its early environment shielded it from later interactions. Perhaps it resided in a low-density region, before being drawn into the Perseus cluster long after its formation. Once captured by the cluster's gravitational field, it may have been stripped of its outer dark matter halo and gas, leaving only the dense stellar core that persists today. Such a process would have halted further evolution and ensured its stability within the cluster's hot gas-rich environment. In this interpretation, the relic is not only old but orphaned, a remnant nucleus of a once larger system that ceased to grow. The colour of its light reinforces this history. Observed across multiple wavelengths, the galaxy displays a pronounced red hue typical of old stellar populations. Its spectrum is dominated by cooler low-mass stars in late stages of fusion. The absence of emission lines, which would signify hot ionized gas, confirms that no new stars have formed in billions of years. Instead, the light is continuous and smooth, reflecting the combined output of countless aging suns. Infrared measurements add further evidence the galaxy's brightness in those bands is consistent with evolved stars, not with the warm dust that accompanies active star formation. Every observable trait converges on the same conclusion: NGC 1277 is a fossil frozen in light. The processes that once shaped its structure have ended, leaving only slow internal evolution as its stars age and fade. To understand what makes this relic so rare, it helps to consider how few comparable systems exist nearby. Surveys of the local universe have identified only a handful of compact galaxies with similar mass and age characteristics. Most reside in clusters, suggesting that dense environments may play a role in their survival. The Perseus relic is one of the most studied because its proximity allows astronomers to resolve its internal structure with exceptional detail. Each observation refines the understanding of how it differs from normal lenticulars. It lacks the faint outer halos seen around typical early-type galaxies, and its stellar kinematics reveal no evidence of extended components added through later mergers. Even its globular cluster system reflects this simplicity, dominated by red metal. Rich clusters, it lacks the blue metal-poor population that would indicate later accretion of smaller satellites. Every sign points to a system that formed quickly reached maturity early and has remained nearly untouched ever since. The relic nature of the galaxy carries implications beyond its individual story. It provides direct evidence that some early massive galaxies could survive intact to the present day, challenging assumptions that all such systems were transformed. By comparing its properties to those of distant compact galaxies observed at redshifts greater than 2 astronomers test theories of galaxy formation and feedback. If NGC 1277 truly represents an ancient survivor, it demonstrates that the basic building blocks of modern ellipticals were already in place when the universe was still young. The key difference is that this system never underwent the secondary mergers that built extended envelopes around others. The relic's continued existence implies that certain environments can preserve early structures, offering a rare glimpse of what the cosmos once looked like. when its first massive systems condensed from primordial gas. The surrounding cluster accentuates this contrast between past and present. While most of the Perseus members show signs of transformation, tidal features distorted halos or traces of recent accretion, the Relic remains pristine. Its orbit near the cluster core places it in a region of high gravitational potential, but relatively low probability of direct collisions. The dense intracluster medium acts as both deterrent and preserver, preventing cold gas from accumulating and protecting the compact system from minor encounters that might disturb its symmetry. Over the course of billions of years, this delicate balance has maintained its form. In effect, the galaxy's stillness is reinforced by the cluster's own dynamics. The surrounding energy prevents change, allowing the relic to remain an unbroken relic of a vanished era. The idea of being frozen in time is not metaphorical, but rooted in measurable data. The ages of its stars, determined through spectroscopy, cluster tightly around 12 billion years, with no evidence of younger populations. Its chemical abundance patterns match those predicted for galaxies formed during the peak of cosmic star formation and then rapidly quenched. Even the gradients of metallicity across its disk are shallow, implying that mixing has long since stabilized. This uniformity means that on a galactic scale, evolution has effectively ceased. NGC 1277 continues to orbit within the Perseus cluster, but internally it no longer changes. The processes that drive growth in other systems, merger-induced starbursts, inflows of interstellar gas or tidal distortions are absent. What remains is a structure in equilibrium, balance between gravity and time, preserving the conditions of the universe's youth. To view the compact lenticular today is to observe an ancient equilibrium held within modern surroundings. Its stillness contrasts with the restless energy of the cluster, where gas continues to flow and galaxies continue to merge. The relic's red light cuts through that turbulence as a steady reminder of cosmic longevity. Every photon that escapes its dense core carries information about an age when galaxies were few stars formed furiously, and black holes began to shape the universe's structure. Across the dark expanse of the Perseus cluster, this small ancient survivor endures unchanged, unmoving a lens through which the deep past remains visible. NGC 1277, in its quiet persistence, holds within its light the memory of stellar birth that ended almost as soon as it began. Its stars, formed during the universe's first few billion years, constitute one of the oldest known populations in any nearby galaxy. When astronomers dissect its light with spectrographs, they find the unmistakable fingerprints of chemical enrichment that occurred with extraordinary speed. Elements such as magnesium, calcium, and silicon, known as alpha elements, are present in proportions that reveal a brief but intense epoch of star formation dominated by massive short-lived stars. These elements arise from core collapse supernovae explosions that follow the deaths of the most massive suns, each enriching the surrounding gas with newly forged metals. The overabundance of these alpha elements relative to iron indicates that the starburst which built the Relic galaxy must have lasted less than 1 billion years. In that short period, the interstellar gas was converted into stars so rapidly that the slower iron-producing supernovae of later generations never had time to contribute in full. When the gas finally ran out or was expelled, the process ended abruptly, leaving behind a stellar population frozen in chemical maturity. The age of this population is determined through precise comparison between observed spectra and theoretical models of stellar evolution. By analyzing the strength of absorption lines in the visible and near-infrared bands, astronomers can infer the average age and metallicity of the stars. For NGC 1277, these models consistently point to formation epochs exceeding 12 billion years ago, corresponding to redshifts greater than 2 when the universe was less than 2 billion years old. This places the Relic among the earliest large systems to have formed contemporary with the epoch when the cosmic star formation rate reached its peak. In that era, cold gas collapsed under intense pressure, feeding starburst galaxies that shone brightly in the infrared. The Relic appears to have been one such galaxy, but unlike its distant counterparts, it survived to the present without being subsumed into larger structures. The result is a nearby time capsule that records in detail how the first massive galaxies assembled and aged. The uniformity of its stellar population is striking. Across the entire disk, observations reveal only minimal variation in colour and spectral features. There are no gradients of age or metallicity that would indicate successive generations of star formation. Every region from the bright central bulge to the outer edge bears the same signature of ancient metal-rich stars. This homogeneity implies that the burst of star formation that built the Relic occurred nearly simultaneously throughout its structure. The gas must have been well mixed, collapsing inward under gravity, and cooling uniformly as it transformed into stars. Such efficiency is rare in modern galaxies where star formation proceeds in clumps and cycles. In NGC 1277, it was as if the entire system ignited at once, and then fell silent forever. The compact nature of the galaxy enhances this impression of rapid coordinated formation. In a smaller volume, gas densities would have been extremely high, allowing cooling times to shorten and star formation rates to soar. The feedback from supernovae would have quickly heated or expelled the remaining gas, preventing any further starbirth. Once the initial generation of massive stars ended their lives in explosive deaths, the energy released would have been sufficient to clear the remaining interstellar material from the galaxy's potential well. What remained was a dense gas-poor core filled with aging stars. Over billions of years, the absence of new material preserved that configuration, while gravitational relaxation smoothed the orbits into a stable equilibrium. The lenticular fossil visible today is the direct consequence of this early self-limiting process, intense creation, followed by enduring quiet. Chemical evidence further supports the notion of a brief early burst. Ratios of alpha elements to iron peak at values higher than in the Milky Way, and the total metallicity approaches the upper limits observed in any galaxy. This indicates that NGC 1277's interstellar medium was enriched rapidly and completely before star formation stopped. Subsequent lack of accretion from the surrounding cluster prevented dilution by metal-poor gas. The resulting stellar population is both old and chemically mature, a unique combination that marks the Relic as a closed system. Even today, its stars show little trace of the gradual chemical evolution seen elsewhere. In this sense, the Relic functions like a sealed archive, its composition fixed, since an era when the first heavy elements were spreading through the cosmos. The study of such chemical signatures provides a direct link to the conditions of the early universe. When compared with distant high redshift galaxies, NGC 1277's spectrum matches those of compact quiescent galaxies observed with the James Webb Space Telescope. These distant analogues exist at a time when the universe was less than 1/5 its current age, and they display similar metallicities and stellar mass densities. The Relic in Perseus is thus a local counterpart, offering a resolved close-up view of what those ancient systems would become if left untouched. Its existence confirms that at least some early galaxies could reach maturity quickly and remain stable for the rest of cosmic history. The stars within it, each now billions of years old, continue to shine faintly in unison, forming a population as close to immortal as stellar physics allows. Understanding how such a rapid transformation occurred has become central to the study of galaxy evolution. The prevailing view holds that the compact relic formed from the catastrophic collapse of a massive gas-rich cloud early in cosmic time. In this event, cold streams of primordial gas funneled into a small region, igniting star formation at extreme rates. Radiation pressure, stellar winds, and supernova explosions quickly built up turbulence, driving the remaining gas outward and ending further starbirth. The result was a compact stellar system dominated by old metal-rich stars and devoid of the raw material needed for renewal. Subsequent growth through mergers which would normally follow never came. Perhaps the galaxy's early environment lacked nearby companions, or perhaps it was ejected from its initial group before mergers could occur. Whatever the reason, the compact remnant remained isolated long enough for its internal structure to settle into the tranquil configuration observed today. The relic's chemical uniformity also helps explain its current color and luminosity. As its stars age, they grow cooler and redder, emitting most of their light in the visible and near-infrared. The combined spectrum resembles that of an old elliptical galaxy, but confined to a smaller, denser body. Because no young blue stars replenish the brightness, the galaxy's overall luminosity slowly fades, while its color shifts further toward the red. This slow dimming, ongoing for billions of years, gives NGC 1277 the muted appearance that distinguishes it from its brighter, more active neighbors. Yet beneath this subdued glow lies immense density, a concentration of mass that continues to bind the system with unyielding gravity. Each star orbits within a field shaped by billions of others, their combined motions forming a silent rhythm that has persisted since before Earth existed. The study of such ancient light provides more than a snapshot of a bygone era. It connects directly to the processes that shaped the visible universe. By measuring the relic's metallicity, velocity, dispersion, and age, scientists reconstruct the timeline of star formation and feedback that once dominated the cosmos. Every spectral line acts as a fossil imprint of conditions that no longer exist: high gas densities, rapid enrichment, and violent outflows. Through NGC 1277, the distant past becomes tangible, a nearby relic of a time when galaxies were born in fire and then cooled into enduring silence. In the deep heart of the Perseus cluster, surrounded by the glow of hot plasma and the slow drift of larger companions, the compact fossil continues to shine its light, carrying the chemistry of the early universe across space and time. NGC 1277 rotates with a precision that betrays the internal harmony of its stars. In images it seems static, yet behind that calm facade lies an intricate ballet of motion. Spectroscopic mapping shows that the relic spins rapidly around its short axis, with stars near the mid-plane moving at hundreds of kilometers per second. This rotation, measured through subtle shifts in wavelength, reveals that the compact system retains the angular momentum of its earliest formation. It is a rare survivor of an age when galaxies condensed from turbulent gas clouds and began to spin as they cooled. In most systems, later mergers or accretion altered these patterns, thickening disks and changing rotation curves. The lenticular fossil, by contrast, still follows the same rhythm set billions of years ago. Each orbiting star is part of an ancient mechanism balanced between ordered motion and random velocity dispersion, the latter rising sharply toward the center where gravity dominates. The result is a stable configuration in which stars flow around the core like particles within a self-contained whirlpool of light. Astronomers have long sought to understand how such compact galaxies maintain both high rotation and extraordinary density. Detailed observations from instruments such as the Keck Observatory's integral field spectrographs have mapped the velocity field across the entire relic, revealing a sharp transition between rotation-dominated outer regions and dispersion-dominated inner zones. The outer stars follow near circular paths that preserve the disk's flattened shape, while those closer to the centre move in all directions, bound more by the collective gravity than by angular momentum. This blend of dynamics marks the system as lenticular rather than purely elliptical. It rotates fast enough to suggest a disk origin, but lacks the spiral structure or star-forming regions that would make it a true spiral. The relic stands at the boundary between forms a frozen hybrid that no longer evolves. The measurement of these internal motions depends on the interpretation of spectral lines, particularly those of magnesium and iron, which shift in response to the Doppler effect. By analysing how these lines broaden and tilt across different positions, astronomers construct maps of stellar velocity and dispersion. The resulting data reveal a rotation curve that peaks at about 200 to 300 kilometers per second, before declining toward the outermost detectable regions. This profile mirrors that of more massive galaxies, but compressed into a smaller radius, underscoring the relic's extreme compactness. The central velocity dispersion exceeds 300 kilometers per second, among the highest recorded for a galaxy of its size. Such figures imply an enormous concentration of mass in the nucleus, later confirmed through dynamical modelling, to be consistent with a supermassive black hole at its heart. Even without direct imaging of that core, the motions of the surrounding stars trace its gravitational influence. The structural geometry of the galaxy supports this interpretation. Its photometric profile follows a near-perfect symmetry, about the rotational axis indicating long-term stability. No significant tidal distortions or asymmetries are visible, a sign that external forces have not perturbed it for many billions of years. The stars occupy a thickened disk embedded within a compact bulge, with the disk's plane inclined slightly relative to our line of sight. This orientation allows astronomers to measure its internal kinematics with precision. The absence of dust ensures that starlight passes unimpeded, offering an unobscured view into the stellar distribution. In most galaxies, gas and dust complicate such analysis, scattering light and introducing irregularities. In the Perseus relic, the scene is almost ideal, a clean, transparent system that reveals its internal order with exceptional clarity. The transition from rotation-dominated to dispersion-dominated motion inside the compact relic illustrates a key principle of galactic dynamics. In the outer regions, stars behave like planets around a distant sun, orbiting within a relatively thin plane. Closer to the center, gravitational interactions among billions of stars create a more isotropic field, where orbits become randomized. This inner mixing contributes to the galaxy's stability by preventing any single direction of motion from dominating. Over time, the combination of ordered and chaotic movement produces a smooth velocity distribution that resists collapse or expansion. Such equilibrium is maintained only in systems that have remained undisturbed for immense periods. Any recent merger or tidal encounter would disrupt it, introducing asymmetries in the velocity field. The perfect regularity of NGC 1277's motion is thus another sign of its long isolation. Rotation also provides clues to its formation. In the early universe, galaxies acquired angular momentum through gravitational torques exerted by neighbouring structures. Those that formed in denser environments tended to spin faster, as collapsing gas conserved its momentum while cooling. The relic's high rotation rate suggests that it condensed from a strongly spinning cloud, collapsing rapidly while retaining the bulk of its angular momentum. As star formation consumed the gas, the remaining material settled into a flattened disk, producing the lenticular shape we see today. Because no subsequent accretion added misaligned components, the original spin axis has remained constant. This continuity of rotation across billions of years reinforces the idea of an untouched system preserved from a much earlier epoch. When astronomers map the brightness distribution across the galaxy, they find that its isophotes contours of equal light are nearly circular in the inner regions and slightly elongated outward. This geometry reflects both its rotation and intrinsic flattening. The axis ratio between minor and major axes confirms that it is not purely spherical, but subtly disc-like. Photometric decomposition shows a small central bulge superimposed on a fast-rotating disk, both composed of the same old metal-rich stars. The bulge contributes most of the central light, while the disk defines the outer structure. This dual composition hints at a formation process that involved both dissipative collapse, which built the bulge, and rotational stabilization, which preserved the disk. Over time, without fresh gas to thicken it, the structure settled into its current form, compact, smooth, and enduringly stable. The stellar motions within NGC 1277 also provide insight into its mass-to-light ratio, a measure of how much unseen matter contributes to its gravitational field. Dynamical models derived from its velocity data indicate that the visible stars account for nearly all the mass within the central few kiloparsecs. Unlike typical galaxies which require large dark matter halos to explain their rotation curves, the Relic's motions can be described almost entirely by its stellar content and a central black hole. This finding adds to the debate about whether NGC 1277 is truly dark matter deficient, or whether its compact size simply hides the halo's influence beyond the observable region. Regardless, within the luminous portion, the dynamics remain dominated by stars, making it an unusually self-contained system in both structure and motion. The enduring order of this rotation invites comparison to cosmic timepieces. Each orbit of a star around the galaxy's center may take tens of millions of years, yet in the age of the universe, billions of such revolutions have passed. Through them all, the galaxy's shape and spin have scarcely changed. The forces that might alter its rotation, mergers, tidal stretching, or new star formation, have long been absent. What remains is an island of constancy amid the cluster's turbulent environment, a relic not only of early formation but of enduring balance. In its silent spin, NGC 1277 records both the energy of its birth and the stillness of its long survival, a compact engine turning steadily beneath the vast hot halo of the Perseus cluster. NGC 1277 is surrounded by a population of globular clusters that orbit like distant satellites around a long-forgotten world. These dense star clusters, each containing hundreds of thousands of ancient suns, serve as witnesses to the galaxy's earliest formation. Their number, color, and distribution provide insight into the conditions that shaped the compact relic billions of years ago. Observations show that the system is dominated by red metal-rich clusters, with only a small fraction of blue metal poor ones. This imbalance sets the relic apart from most galaxies of comparable mass, which typically possess bimodal cluster populations. The preponderance of red clusters indicates that nearly all of them formed during a single brief chemically enriched phase, likely coinciding with the same intense burst of star formation that built the galaxy's stars. The scarcity of blue clusters, which generally form in metal-poor environments or through later accretion of smaller companions, supports the view that NGC 1277 has remained isolated since its creation. Its globular cluster system, like the galaxy itself, speaks of early completeness followed by enduring quiet. Globular clusters are among the oldest bound structures in the universe. Their compact cores of tightly packed stars are fossils from the epoch when galaxies first assembled. By studying them, astronomers can trace the evolutionary pathways of their host systems. In NGC 1207's case, the evidence is unusually clear. Nearly all clusters share the reddish hue of the parent galaxy's stars, and their metallicities indicate formation in an already enriched environment. This means the interstellar medium from which they condensed had been processed by several generations of massive stars, consistent with a rapid and efficient cycle of enrichment. The absence of metal-poor clusters suggests that by the time the galaxy's globulars formed, it had already reached a mature chemical state. In other galaxies, later mergers often introduce new bluer clusters formed in primitive systems, but no such secondary population is visible here. The Relic's cluster family is homogeneous and ancient, another sign of arrested development. The spatial distribution of these clusters also reinforces the impression of compactness. They are concentrated close to the galaxy's center following the steep decline of its stellar light. The system lacks the extended halo of globulars that surrounds most massive ellipticals, where outer clusters trace the remains of accreted satellites. Instead, the clusters around NGC 1277 form a dense, centrally bound swarm confined within a few tens of thousands of light years. This concentration implies that the Relic never underwent major mergers capable of scattering clusters to large distances. It also indicates that its gravitational field has remained largely unaltered since their formation. The clusters move within a potential dominated by the galaxy's stellar mass and central black hole orbiting in paths that mirror the symmetry of the main body. In such stability, they have circled the galaxy for billions of years without significant loss or disruption, their compactness preserving the same quiet order seen throughout the system. Photometric surveys using the Hubble Space Telescope have catalogued hundreds of these clusters, each appearing as a faint, unresolved point of light against the dark sky. The ratio of clusters to the total stellar mass, the specific frequency, is unusually low compared with typical early-type galaxies. This means that for its size, the Relic hosts fewer clusters than expected. The low frequency may be another consequence of its truncated evolution. If the galaxy formed all its stars and clusters in one short burst, there was no later opportunity to build a large extended population through mergers. The few that exist today are survivors of that first violent era. Their ages derived from color magnitude diagrams and spectroscopy exceed 11 billion years, aligning with the age of the galaxy's main stellar population. Together they form an unbroken chain of evidence linking the Relic to the universe's earliest epoch of structure formation. The predominance of red metal-rich clusters tells a story about the conditions inside the young galaxy. During the brief phase of intense star formation, supernovae enriched the gas with heavy elements, raising its metallicity rapidly. Globular clusters that formed in this environment inherited the same chemical composition, becoming redder and more luminous. The few blue clusters may have originated slightly earlier before enrichment was complete, or in small satellite fragments that were later absorbed. However, their scarcity and close binding indicate that, even if minor accretion occurred, it was negligible in scale. Unlike the sprawling halos of giant ellipticals where tidal interactions add new clusters over time, NGC 1207's cluster population reflects self-contained formation. Each cluster is a relic within a relic, a miniature fossil echoing the rapid creation and subsequent stillness of its host. Spectroscopic measurements of the cluster's radial velocities reveal that they share the same general rotation as the galaxy's stars. This coherence suggests that they formed from the same angular momentum field and have retained it since. Their motion is orderly, not random, confirming that the system has not been significantly disturbed by mergers or strong tidal interactions. The clusters closest to the center move faster, influenced by the steep gravitational gradient of the compact stellar mass and the central black hole, while those farther out trace slower, wider paths. Despite the cluster's motion through the Perseus environment, this internal order remains intact. The gravitational pull of the relic is strong enough to hold its cluster population together, even as the surrounding intracluster medium exerts constant pressure. In other galaxies, globular clusters often record multiple waves of accretion and star formation, forming a historical archive of assembly. Blue clusters are typically associated with early metal-poor halos, while red ones correspond to later enriched bulge formation. The near absence of blue clusters in NGC 1277 means that its entire history may have unfolded within a single generation. This simplicity is both rare and instructive. It provides a clean laboratory for understanding how the first massive galaxies formed their cluster systems without later interference. The Perseus relic, free from the complications of mergers, offers a direct window into primordial cluster formation mechanisms. Its cluster's uniform metallicities and compact arrangement match predictions from early universe simulations, where high gas pressures in dense, rapidly collapsing environments yield tightly bound metal-rich clusters in short timescales. Astronomers use globular clusters as tracers to estimate the galaxy's mass distribution beyond regions where starlight is easily measured. By modelling their velocities and spatial density, researchers can infer how mass is distributed through the outer halo. In NGC 1277, these analyses reinforce the finding that the stellar component dominates the gravitational potential, even far from the centre. The clusters orbit in a field consistent with a minimal contribution from dark matter, adding another dimension to the debate over the relic's apparent deficiency. The same measurements also confirm that the system has remained dynamically undisturbed for more than 10 billion years. Each cluster's orbit repeats endlessly, tracing a stable path through a gravitational field that has changed little since its origin. The enduring presence of these clusters transforms the galaxy into more than a single object. It is a miniature ecosystem of ancient stars and orbits, enclosed within the cluster's wider sea of plasma. In the dim light of the Perseus core, the red clusters shimmer faintly, each a dense concentration of a light, formed in the same epoch that gave rise to the galaxy itself. They circle silently, their combined motion, mirroring the balance of forces that hold the entire relic together. Across cosmic time, they have survived radiation gravitational tides and the slow erosion of the cluster environment. The faint glow of each one contributes to a halo of ancient light around the lenticular fossil, an outer memory of its first and only act of creation. Around this still compact heart of stars, the globular clusters endure as steadfast companions, quiet, metal-rich, and as ancient as the galaxy that gave them birth. NGC 12b77 carries within its stars the chemical signatures of a past written in light. Each spectral line observed from its surface tells a story of temperature, composition, and pressure woven together into a record of ancient stellar processes. When astronomers speak of its chemistry, they are not describing something abstract, but the literal ingredients from which it was forged. The compact relic stars are rich in metals, astronomical shorthand for all elements heavier than hydrogen and helium, revealing that the gas from which they formed had already been enriched by earlier generations of massive stars. This high metallicity, combined with pronounced alpha element enhancement, points to a formation epoch when the universe was only a fraction of its current age. During that time, star formation in galaxies like this one was an explosive, short-lived event driven by gas collapsing at extraordinary densities. Within less than 1 billion years, this material was converted into stars and enriched by supernova explosions that seeded the entire system with heavy elements. The result was a stellar population born fully mature, its chemistry locked in place before slower evolutionary processes could alter it. The specific ratio of alpha elements to iron in the Relic stars reveals the timing of its starburst. Alpha elements, oxygen, magnesium, silicon, and others are produced in the cores of massive stars and released through core collapse supernovae on timescales of millions of years. Iron, by contrast, is produced primarily by type Ia supernovae that occur in binary systems over hundreds of millions to billions of years. A high alpha to iron ratio therefore indicates that star formation ceased before those slower explosions could contribute significant iron. In NGC 1277, this ratio is unusually elevated, signaling that its stars formed in one rapid generation. The galaxy's chemistry thus encodes not only composition but chronology, a clock frozen in its earliest hour. No subsequent influx of pristine gas diluted that mix, and no second generation of stars altered the record. The chemical uniformity observed today is the direct imprint of that first and final epoch of creation. Across its surface, spectroscopic studies reveal minimal gradients in metallicity. In most galaxies, stars near the centre are more metal-rich than those in the outskirts, reflecting waves of star formation that proceed inward to outward. In the Perseus Relic, this difference is faint, nearly erased by the passage of time. Such flat gradients imply either rapid mixing in the early stages or the absence of prolonged formation afterward. The gas must have been well stirred before converting entirely into stars, producing a nearly uniform chemical composition throughout the disk and bulge. This homogeneity contributes to the galaxy's even coloration, a deep reddish tone that remains constant across its surface. It glows with the hue of old metal-rich stars, cool but enduring their collective light suffused through space, like the last embers of a long-quenched fire. The efficiency of enrichment in this galaxy also hints at extreme physical conditions. To reach such high metallicity in such a short time, star formation rates must have been enormous, possibly hundreds of solar masses per year, within a volume only a few thousand light-years across. The feedback from supernovae would have been violent, releasing enough energy to drive gas out of the system and halt further star formation. What remains today is the aftermath of that violent equilibrium, a dense stellar body enriched beyond what its size might suggest its gas expelled, or heated beyond the ability to cool again. This self-quenching process is one of the leading explanations for how massive galaxies transitioned from blue star-forming systems to red quiescent ones. In NGC 1277, this transition happened so early and completely that no trace of star-forming activity remains. Its chemical record is the echo of a storm that ended before the cluster around it was even born. The metallic richness extends not only through its stars, but also through the few surviving traces of interstellar material. Observations in infrared and millimeter wavelengths reveal almost no cold gas or dust. Yet, where remnants exist, their spectra confirm high concentrations of metals. These traces likely represent material shed by aging stars rather than residual interstellar clouds. The absence of substantial molecular gas means that the galaxy has no reservoir from which to form new stars. Every component from its bright core to its faint periphery is locked in an evolved state. In a cosmic sense, its chemistry has reached equilibrium. No new elements are being synthesized at galactic scale. Only within individual stars does nuclear fusion continue slowly converting lighter atoms into heavier ones, before returning them to the interstellar medium that will never again give birth. The chemical fingerprints of the relic also offer clues about its environment at formation. Simulations of early galaxy assembly suggest that compact systems with rapid enrichment likely formed in dense regions where gas inflows were abundant and collapse times short. The resulting starbursts created high metallicity and alpha enhancement, while subsequent feedback expelled most of the gas. The Perseus relic matches this pattern, exactly implying that it may have originated in a similarly dense protocluster environment. Over billions of years, that region evolved into the modern Perseus cluster, and the relic now drifts within the same cosmic basin where it was born. Its current isolation, far from active star formation, represents the final stage of a process that began in intense compression. Its chemistry records not only what it is made of, but where it came from, a high-density corner of the early universe, where time moved quickly and creation ended early. The study of NGC 1277's composition has implications for models of cosmic chemical evolution. Because its stars formed in a single burst, the galaxy's integrated spectrum provides a clean snapshot of early enrichment. Comparing it with spectra from distant galaxies allows astronomers to calibrate the rate at which metals built up across cosmic time. The relic acts as a bridge between observation and theory, translating faint high redshift data into a tangible nearby example. Its metallicity also helps constrain feedback mechanisms in galaxy formation simulations, particularly those involving supernovae and active black holes. The fact that the relic achieved such enrichment without showing signs of extended star formation suggests that feedback must have been both strong and efficient. Whatever processes halted star birth also trapped the metals inside, preventing them from being expelled into intergalactic space. This retention efficiency remains one of the more puzzling aspects of the relic's chemistry. Despite evidence of violent feedback, it somehow preserved nearly all of its heavy elements within its compact body. Even within the Perseus cluster's complex environment, the relic's chemical fingerprint remains distinct. Nearby galaxies exhibit a broader range of metallicities, reflecting later accretion and mixing with less enriched material. NGC 1277 stands out as chemically complete, a closed system, where enrichment reached its limit and then froze. Its high metallicity gives its light a warm tone that contrasts with the cooler colours of younger systems. When viewed through large telescopes, this difference is subtle but perceptible, like a faint bronze cast against the grey of its neighbours. To astronomers, this glow is not decorative but diagnostic, a visible confirmation of ancient processes concluded long ago. The consistency of this chemical profile reinforces the notion of finality. Every measurement, from elemental abundance ratios to absorption line strengths, aligns with the image of a galaxy that has finished all significant internal evolution. The relic's chemistry has become a fixed language unchanged for more than 10 billion years, carrying forward the story of an era when the universe itself was still young. Through that unchanging light, astronomers glimpse the processes that seeded the cosmos with the building blocks of planets and life. Within the Perseus cluster, surrounded by the energy of active galaxies and the heat of intergalactic gas, NGC 1277 remains silent and complete, a small, dense monument to the universe's earliest and most efficient forge of stars. NGC 1277, despite its mass and density, exhibits an extraordinary absence of later growth. Most galaxies of comparable size and brightness have expanded through the continual accretion of smaller companions or through mergers that deposit new material in their outskirts. Over billions of years, such processes build faint halos of younger stars and stretch galaxies into larger, more diffuse structures. Yet the compact relic has remained nearly unchanged since its early formation. Its surface brightness profile is steep, showing no sign of extended stellar envelopes or tidal debris. The edges of the galaxy fall away sharply, and beyond its luminous boundary lies only the faint background glow of the Perseus cluster. This sharp truncation has led astronomers to describe it as dynamically complete, a system that finished assembling long before the cluster around it reached its current form. The absence of later accretion has preserved its compact dimensions, leaving it as a rare survivor of an earlier cosmic phase, when galaxies were smaller and denser than those observed today. The reasons for this arrested development lie partly in environment. Within the cluster's dense core, interactions between galaxies are frequent in gravitational terms, but rarely lead to mergers. High relative velocities mean that galaxies pass one another too quickly for their mutual gravity to bind them. Instead of coalescing, they exchange tidal forces and continue on their trajectories. For a compact system like NGC 1277, this environment acts as a kind of shield. It prevents slow, gas-rich collisions that would otherwise have built new layers of stars, while the surrounding hot intracluster gas strips away any cold gas that might have been acquired. The result is isolation by motion, constant encounters, but no lasting contact. Over time, the Relic became locked in a cycle of passage through the cluster core, gravitationally stirred but never disrupted. Its small size and high density make it resilient to external tides, and its lack of cold gas ensures that no new material can accumulate. It has been moving within the cluster for billions of years, changing position but not character. Evidence for this long-term stability comes from deep imaging that reveals no visible tidal tails or shells around the galaxy. These structures, common in systems that have merged or absorbed satellites, form when stars from smaller companions are stretched into streams by gravity. NGC 1277 shows no such patterns. Its outer light is smooth and symmetric, unmarked by any trace of recent interaction. Even sensitive observations from the Hubble Space Telescope and the Subaru telescope detect nothing beyond the compact stellar core. The implication is that the Relic has not experienced any significant merger for at least 10 billion years. If it ever possessed an extended halo, it was stripped away long ago, leaving only the dense nucleus. This may explain its current mass-to-light ratio and possible dark matter deficiency. The outer halo, which would have contained most of the dark matter, may have been lost to the tidal field of the cluster. What remains is the luminous skeleton of a once larger system compressed into the form of the Relic we see today. This scenario is consistent with numerical simulations that track the evolution of galaxies within clusters. When a smaller galaxy falls into a massive cluster, the tidal forces can remove its outer layers while leaving its dense core intact. Over multiple passages, the stripped core survives as a compact remnant orbiting the cluster center. If NGC 1277 followed this path, it may once have been the central galaxy of a small group that was later absorbed by Perseus. The stripping process would have removed its dark matter halo and extended stars, leaving behind the dense central bulge formed during its early starburst phase. Such remnants are predicted to be rare but stable, resistant to further change due to their compactness. This explanation aligns with the Relic's current appearance, a galaxy that seems incomplete only because it has been reduced to its most concentrated form. Whether it was always compact or became so through stripping, its long survival demonstrates the resilience of dense stellar systems under the harshest environmental conditions. The lack of new stars in the galaxy confirms that it has been cut off from the cycle of cosmic growth. Spectral analyses show no ultraviolet emission from young stellar populations, and no hydrogen alpha lines that would indicate ionized gas from recent star formation. In the infrared, it remains faint and steady, emitting only the glow of aged stars. The absence of dust further supports this view. Dust grains form in regions of active starbirth and are quickly destroyed in environments lacking replenishment. NGC 1207's complete silence across these wavelengths marks it as one of the most quiescent galaxies known. Its luminosity has declined gradually as its stars aged, yet its structure has remained rigidly fixed. Over the course of billions of years, stellar mass loss from dying stars has added little to its total light or form, as any gas shed in this way is rapidly heated by the surrounding cluster medium and carried away. The galaxy's aging process is therefore one of slow fading, rather than change a passive drift toward lower brightness without renewal. The notion of a galaxy deprived of growth raises questions about its long-term fate. Without mergers, accretion, or star formation, NGC 1277 will continue to dim until its stars evolve into faint remnants, white dwarfs, neutron stars, and black holes. On cosmological timescales, its light will weaken even as its mass remains bound by gravity. The Relic will persist as a compact collection of stellar remnants orbiting a central black hole still dense but almost invisible. In this sense, it offers a glimpse of the universe's distant future, when star formation everywhere will cease, and galaxies will fade into dark configurations. The Relic is already far along that path, a preview of what the cosmos will eventually become when its creative energy is exhausted. Its lack of evolution also provides scientists with a reference point for measuring change elsewhere. By comparing the Relic to galaxies that have continued to grow, astronomers can separate the effects of environment from those of internal physics. The differences in structure, metallicity gradients, and dark matter content all point to the role of early conditions in determining galactic fate. NGC 1277 exemplifies how a single burst of star formation, followed by environmental isolation, can produce a galaxy that endures without transformation. It is both an anomaly and a benchmark demonstrating the full range of outcomes that cosmic evolution can produce. The stillness of this galaxy contrasts sharply with the ongoing turbulence of its surroundings. The Perseus cluster continues to evolve through infalling galaxies, merging subgroups as energetic outflows from its central black hole. Streams of gas and stars stretch between members, evidence of continual rearrangement. Amid that dynamic backdrop, the Relic moves quietly, maintaining its compact form while all else changes around it. Its orbit through the cluster carries it through regions of varying density and radiation, yet no measurable alteration occurs. To watch it is to see persistence embodied, a dense knot of light unaltered by the forces that sculpt the cosmos. Over billions of years, such stability turns into a kind of invisibility. The Relic is easy to overlook among the cluster's brighter, more complex members. Yet within that stillness lies the key to understanding how galaxies might endure without growth. It stands as a testament to what happens when evolution stops, when a system becomes so self-contained that time itself seems to pass around rather than through it. NGC 1277 remains what it has been since near the dawn of galactic history. Small, dense, and complete an island of ancient starlight, orbiting through a sea of change. Its continued existence within the Perseus cluster reminds astronomers that the universe's history is not a single narrative of growth and expansion, but a collection of parallel stories, some of birth and transformation, others of endurance and stillness. The Relic belongs to the latter, a cosmic survivor, whose silence speaks of the earliest chapters of creation and the long, unbroken continuity of light. NGC 1277 has become the center of an ongoing debate about the invisible matter that underlies all galaxies. Observations suggest that this compact system may contain little to no dark matter, within its visible boundaries a claim that challenges one of the foundational assumptions of cosmology. In most galaxies, dark matter outweighs the stars by large factors and extends far beyond the luminous disk or bulge. Its gravitational influence is detected through the rotation of stars and gas, which remain moving faster than visible mass alone can account for. Yet in the Relic galaxy, stellar velocities appear to match the mass inferred from starlight alone. If confirmed, this would make NGC 1277 one of the first massive galaxies known to lack a substantial dark matter halo, an anomaly that has prompted both skepticism and fascination. Whether this absence is intrinsic or the result of environmental stripping remains one of the most actively studied questions in extragalactic astronomy. The measurement of dark matter in any galaxy relies on tracing the motion of stars and other traces across its extent. In NGC 1277, detailed kinematic maps derived from integral field spectroscopy reveal a steeply rising velocity curve that flattens at small radii but does not continue upward in the manner expected if a dark halo were present. This means that the gravitational potential is dominated by visible mass, particularly within the central few thousand light-years where observations are most precise. Beyond that range, the signal becomes faint, and the galaxy's compactness makes further measurement difficult. For most galaxies, extended rotation curves are obtained by observing neutral hydrogen gas far from the center, but the Relic contains no gas. As a result, the true outer profile of its gravitational field remains uncertain. Some astronomers argue that dark matter must exist farther out beyond the region now observable, while others propose that the galaxy genuinely lacks a halo because it was stripped away during its history within the cluster. The stripping hypothesis finds support in simulations of galaxy interactions. When a smaller galaxy falls into a cluster's gravitational well, the surrounding tides can remove its dark matter before significantly affecting its stellar core. Because dark matter is more diffuse and less tightly bound, it is the first component to be lost. If NGC 1277 entered the Perseus cluster, early, repeated tidal encounters could have peeled away its halo while leaving the dense stellar system intact. In this scenario, the Relic's dark matter still exists, but is now part of the cluster's diffuse background spread across millions of light-years. The galaxy's visible form would then represent only the surviving nucleus of a once larger system. This idea fits well with the galaxy's current size and the absence of extended halos or tidal debris. The compact remnant would be a stripped core orbiting in a sea of dark matter that no longer belongs solely to it. An alternative explanation is that the Relic never possessed much dark matter to begin with. In some early formation models, galaxies that formed exceptionally early in dense environments could convert nearly all available gas into stars before their dark matter halos fully developed. The intense baryonic collapse would then dominate the gravitational potential, leaving little room for a dark component within the visible radius. Under this interpretation, NGC 1277 might represent a primordial mode of galaxy formation, one in which baryonic matter temporarily overwhelmed the dark matter framework. Such galaxies would be rare and short-lived as later mergers typically rebuild the missing halos, yet the Relic's survival suggests that at least one such object endured unchanged from the early universe to the present day. The possibility that it retains this early configuration makes it invaluable for testing cosmological models, particularly those predicting the coupling between baryons and dark matter during the first stages of structure formation. Direct observation cannot yet distinguish between these scenarios, but each offers insights into how galaxies and their halos interact. If tidal stripping is responsible, NGC 1277 serves as evidence of the destructive power of cluster environments where dark matter can be redistributed among members over time. If intrinsic deficiency is the answer, the relic demonstrates that early universe conditions allowed for more varied pathways of galaxy formation than previously believed. In either case, the compact lenticular becomes an exception that defines the rule. Its dynamics force astronomers to refine their understanding of how visible and invisible matter coexist. The delicate balance seen in most galaxies where dark matter provides structure, while stars supply light, appears in this one to have been broken, leaving a self-gravitating stellar system with little external scaffolding. To measure such subtle distinctions, astronomers rely on the interplay between observation and modelling. High-resolution spectroscopy allows them to map stellar velocities, while sophisticated dynamical models estimate the mass required to produce those motions. In the Relic, these analyses consistently yield mass-to-light ratios close to those expected for purely stellar populations. The models reproduce the observed velocity dispersion without invoking a large halo, a result that holds across multiple independent studies. Some discrepancies remain, especially regarding assumptions about the initial mass function of the stars, which affects how total stellar mass is calculated. A heavier initial mass function could mimic the gravitational effect of dark matter by adding unseen low-mass stars to the total. Yet even when these uncertainties are considered, the Relic still appears unusually baryon-dominated. Within its bright core, nearly all gravitational force arises from the stars themselves, and the central black hole leaving little room for a hidden component. This finding challenges the standard picture of galaxy formation embedded in the cold, dark matter paradigm. According to that framework, dark matter halos form, first providing the gravitational wells that attract gas and allow stars to form. Every galaxy, regardless of size, should therefore be surrounded by a halo that extends far beyond its visible limits. To encounter one that apparently does not follow this pattern is to glimpse an exception that might reveal the limits of the model, or at least its complexity. Some researchers suggest that the Relic's case underscores the diversity of outcomes possible within the same cosmic framework, rare but instructive deviations rather than outright contradictions. Others argue that such systems may hint at processes not yet fully captured by simulations such as extreme feedback or early baryonic collapse that temporarily decouples luminous and dark matter. Whatever the explanation, the Relic galaxy has forced theorists to look more closely at how universal their assumptions truly are. The potential absence of dark matter also affects the galaxy's long-term stability. Without an extended halo to shield it from external influences, the stellar system would be more vulnerable to tidal forces, yet the Relic shows no signs of disruption, implying that its compactness alone provides sufficient binding. The dense central mass acts as its own fortress, preventing stars from being stripped, even as it moves through the cluster's gravitational tides. The system is in effect a self-contained sphere of gravity sustained entirely by its visible matter and central black hole. This intrinsic strength may explain its survival, despite the hostile environment of the cluster core. Where lighter systems are torn apart, the Relic endures. As the debate continues, the Perseus Relic stands as both puzzle and proof. It demonstrates that the relationship between visible and invisible matter is more nuanced than a single model can describe. Whether its halo was lost, never formed, or remains hidden beyond current detection, the fact that such a compact massive galaxy exists challenges the simplicity of cosmic uniformity. In its quiet orbit through the hot gas of Perseus NGC 1277 carries this unresolved question like a silent argument inscribed in starlight, a question about what holds the universe together and what happens when one of its fundamental components appears to be missing. The Relic's stillness conceals a mystery as deep as the cluster that surrounds it, a riddle written not in motion but in the absence of what cannot be seen. NGC 1277 reveals its inner structure through the motions of its stars, the only traces left to measure what lies at its heart. Without gas or dust to map rotation directly, astronomers turn to starlight itself, splitting it into spectra to read velocity shifts and dispersions. Each photon carries a subtle signature of motion, and when combined across thousands of stars, those signatures build a map of gravity. From these maps emerges a detailed picture of how mass is distributed within the compact relic. The stars near its outer edge move rapidly bound by the total stellar mass, but as the view moves inward, velocities rise sharply, reaching values that can only be explained by the pull of a central mass far exceeding that of any single star cluster. This steep gradient in velocity dispersion marks the sphere of influence of a supermassive black hole, a gravitational engine buried at the galaxy's center. Measuring its strength and extent has become one of the main challenges in understanding NGC 1277 and its extraordinary properties. The technique used to probe this region is called stellar dynamical modeling. It involves measuring how light from the galaxy broadens in wavelength due to the random motions of its constituent stars. The wider the lines, the greater the dispersion, and thus the stronger the gravity required to confine them. Observations from the Keck Observatory and the Hobby Eberly telescope have provided such data with sub-arc second precision, revealing velocity dispersions exceeding 300 km per second at the core. These values are among the highest recorded for a galaxy of this size. When converted into a dynamical mass, they imply the presence of a black hole containing billions of solar masses. Early analyses place that mass at nearly 10 billion, a figure that, if correct, would make the Relic's central object one of the most overmassive black holes relative to its host ever discovered. Later observations with improved modeling and higher spatial resolution reduced the estimate but did not erase the mystery. Even at lower bounds, the black hole remains an enormous fraction of the galaxy's total mass, hinting at a relationship between extreme compactness and black hole dominance. The sphere of influence of such a black hole extends only a few hundred light-years, yet within that space, gravity overwhelms the motions of stars. Their orbits no longer follow the general rotation of the galaxy, but respond directly to the central mass. By mapping these changes in dispersion, astronomers can estimate the black hole's effect even without seeing it. In NGC 1277, the transition from rotational to random motion occurs rapidly, suggesting a compact but powerful gravitational well. The stars near the core move at speeds that can only be sustained by a central object of immense density. Beyond this region, their motion settles into the broader pattern defined by the stellar population. The galaxy's equilibrium between these two regimes, local dominance by the black hole and global balance by the stars, illustrates how gravity structures the Relic at every scale. Yet measuring such extremes is fraught with uncertainty. The challenge lies in disentangling the gravitational influence of the black hole from that of the surrounding stars. Both contribute to the observed velocity field, and small variations in the assumed stellar mass-to-light ratio can shift the inferred black hole mass dramatically. Furthermore, the compact size of the galaxy means that even the best telescopes struggle to resolve the very center where the signal is strongest. Adaptive optics and space-based imaging help, but a definitive measurement awaits the next generation of observatories. The Hubble Space Telescope has provided key data, yet its resolution barely reaches the necessary scale. Instruments like the James Webb Space Telescope and future extremely large ground-based telescopes will refine these measurements, possibly confirming whether the black hole truly ranks among the most massive known. The existence of such a large black hole in such a small galaxy carries profound implications. In most galaxies, the mass of the central black hole correlates with the mass of the surrounding stellar bulge. This relationship, known as the M-sigma relation, holds across a vast range of systems and serves as evidence of coevolution between black holes and their hosts. NGC 1277 appears to sit far above this trend, meaning its black hole is disproportionately massive for its stellar population. If the early estimates are correct, it may contain more than 10% of the galaxy's total mass, whereas typical values are less than 1%. Such an anomaly raises questions about whether the galaxy's growth stopped early, while the black hole continued to accrete matter, or whether both formed rapidly together before all growth ceased. The Relic thus challenges the simplicity of coevolution models, suggesting that in some cases black holes can outpace the galaxies that surround them. One hypothesis proposes that during the galaxy's initial starburst phase, gas inflows fed the central black hole as efficiently as they formed stars, leading to parallel rapid growth. When feedback from the black hole's radiation and winds became strong enough, it expelled the remaining gas, halting both star formation and accretion. This feedback-driven quenching would leave behind a mature stellar system and an already massive black hole, both evolving passively thereafter. The Relic's current inactivity supports this scenario. No jets, no accretion, disks, no observable outflows, only the gravitational presence of the dormant engine. Its immense mass combined with the absence of current activity demonstrates how quickly and completely such systems can burn through their available fuel. In cosmic terms, NGC 1277's black hole is ancient and retired a monument to an early epoch of furious growth. Another explanation places the anomaly in the galaxy's history of stripping. If NGC 1277 once belonged to a larger system whose outer layers were removed by the Perseus cluster's tides, its black hole would now appear overmassive only because the surrounding stellar envelope is missing. The ratio of black hole to stellar mass would then be artificially inflated, not because the black hole is unusually large, but because the galaxy is unusually small. This interpretation aligns with models where compact remnants of larger galaxies become cluster cores, their central black holes intact, but their light diminished. Whether intrinsic or environmental, the overmassive black hole remains a defining feature of the Relic and a key to its identity as a fossil galaxy. The effect of this central mass extends far beyond its immediate surroundings. Even though it is now quiescent, the black hole shapes the galaxy's structure through its gravitational field. It anchors the stellar orbit, stabilizes the velocity dispersion, and may influence the long-term survivability of the Relic against external tides. Its immense binding energy ensures that the compact system remains intact even without a massive dark halo. In this sense, the black hole acts as both heart and skeleton, the single force holding the galaxy together as it drifts through the cluster's core. Its presence is invisible in direct light, but manifests through motion, every star's path a faint echo of the gravitational power beneath. Over time, the black hole and the Relic have reached equilibrium. There is no remaining gas to feed further accretion, and the stellar population has settled into stable orbits that no longer change. The central mass now sleeps, radiating neither light nor heat, its event horizon absorbing all that comes near, but finding little to consume. Around it, the stars continue their silent revolution, unaware of the void at their center. The galaxy as a whole remains still preserved by gravity and by absence a perfect balance between creation long ended and destruction not yet begun. In that balance lies the enduring character of NGC 1277, a compact relic whose heart once blazed with unimaginable energy and now endures as a shadow of that vanished fire, quietly holding the memory of its own beginning. NGC 1277's gravitational heart defines not only its core, but the limits of what can be known about such compact systems. Astronomers describe a region around every black hole called the sphere of influence, where its gravity dominates over that of the surrounding stars. In this Relic galaxy, that sphere extends for only a few hundred light-years, a small distance on galactic scales, but immense in its consequences. Within it, stellar orbits are reshaped into steep elliptical paths, and velocity dispersions climb to their highest values. Beyond it, the collective pull of billions of stars takes over, smoothing the galaxy's overall rotation. Measuring this boundary is essential to separating the mass of the black hole from that of the stars, yet it lies near the edge of what current instruments can resolve. Even the best adaptive optics can barely distinguish details at that scale for an object over 200 million light-years away. As a result, every model of the Relic's interior carries uncertainty, a delicate balance between what can be observed and what must be inferred. This limitation underscores how difficult it is to study a galaxy whose most critical features are both compact and ancient. In systems filled with gas, astronomers can observe emission lines tracing circular orbits around the black hole. In NGC 1277 there is no such tracer. Its stellar population is entirely old, its light continuous rather than line-emitting, forcing observers to rely on subtle, broadening of absorption features. These lines carry information about average velocities, but the exact distribution of orbits, how many stars move in circular paths versus random ones, remains uncertain. Different assumptions about these distributions yield different black hole masses. Some models emphasize ordered rotation, producing smaller black hole estimates, while others assume more random motion, increasing the inferred mass. Both reproduce the observed light profile with acceptable accuracy, leaving ambiguity at the center. The Relic's simplicity paradoxically creates complexity for those who study it. In being so clean and featureless, it provides fewer clues. Despite these uncertainties, the velocity data reveal an unmistakable pattern, a sharp peak in dispersion near the core followed by a rapid decline outward. Such a profile can be reproduced only by a concentrated central mass. It is this shape that convinced astronomers that the galaxy hosts one of the most massive black holes relative to its size. In typical galaxies, dispersion decreases more gradually, blending into the contribution from dark matter at large radii. In the compact Relic, the decline happens quickly, indicating that almost all mass is contained within the luminous body itself. This internal concentration of gravity makes the system self-binding and explains its resistance to external disruption. Within its few thousand light-years, the combined pull of stars and black hole creates a gravitational field strong enough to withstand the cluster's tides, ensuring its stability over billions of years. The modeling of such systems depends heavily on computational techniques developed over decades. By simulating millions of stellar orbits under different mass distributions, researchers generate synthetic velocity maps to compare with observations. For NGC 1277, these models have been refined repeatedly as data improved. Early versions suggested a 10 billion solar mass black hole, later revisions brought that down to 2 or 3 billion, and most recent analyses narrow it further, but still find it unusually large for a galaxy of this scale. Each new measurement reshapes the debate, but not the conclusion. The Relic's central engine is extraordinary. Whether its true mass lies at the high or low end of estimates, it remains an extreme outlier. It serves as an anchor point for theories about how black holes and their host galaxies grow together, or in this case, how one may have grown faster and frozen early. Understanding why such imbalance occurred requires looking back to the epoch when the galaxy formed. In the young universe, gas inflows were intense, and central regions of protogalaxies could feed black holes at near maximal rates. Feedback from this accretion in the form of radiation and winds heated the surrounding gas, potentially quenching further star formation. If NGC 1277's black hole formed quickly and reached massive proportions while the galaxy was still assembling, it might have expelled the remaining gas before the outer parts could grow. The result would be a small, dense stellar system surrounding an outsized black hole. Over time, without further accretion or mergers, the system would remain frozen in that early state. This scenario aligns with observations of high redshift galaxies that appear compact and quiescent, their centers already dominated by heavy black holes only a few billion years after the Big Bang. NGC 1277 may simply be one that survived unchanged to the present. The transition between regions dominated by the black hole and those governed by the stars reveals a structural balance that defines the relic's stability. The sphere of influence acts as a gravitational pivot within. Its stars move independently, while beyond it collective motion prevails. This layered dynamic keeps the galaxy in equilibrium, each part compensating for the other. In systems with abundant gas or external inflows, such balance is constantly disturbed as new material falls inward. In the Relic, no such flux exists. Every orbit is old, every path long settled. Over time, random encounters between stars have smoothed out irregularities, creating a nearly isotropic velocity distribution in the core. The result is a steady state maintained for over 10 billion years, a cosmic structure that has found its equilibrium and held it without change. Astronomers measure not only velocities but also higher-order moments of the line-of-sight distribution, subtle asymmetries that reveal whether motion is more tangential or radial. In NGC 1277, these moments indicate a preference for rotation in the outer disk, and more chaotic movement near the center. Such patterns are consistent with the galaxy that once possessed gas-driven rotation, but lost it early, leaving stars to orbit under their own momentum. The randomization near the black hole reflects gravitational scattering over immense timescales, where close encounters between stars redistribute energy and angular momentum. This process, known as relaxation, proceeds slowly in most galaxies, but is accelerated in dense environments. The relic's extraordinary density means that its inner regions may have reached partial relaxation, smoothing stellar motion into near-perfect symmetry around the black hole. These observations allow astronomers to map not only the present, but also the timeline of dynamical evolution. The compact galaxy shows every sign of being old, but its continued stability suggests that internal mixing has long been complete. Its velocity field lacks disturbances, asymmetries, or kinematic twists, implying that no recent mergers or perturbations have occurred. The absence of such irregularities further supports its status as a fossil from the early universe. The structure has endured without renewal or damage, its central black hole acting as both origin and anchor. The light that reaches Earth today carries the cumulative record of that equilibrium motion, without change, rotation, without evolution, gravity in perfect balance with time. The challenges of observing such precision have not diminished its importance. Each new instrument adds detail to the portrait, refining the balance between black hole stars and relic structure. High-resolution spectroscopy continues to push limits, revealing finer gradients in velocity dispersion and improving constraints on mass distribution. Future interferometers and space telescopes will likely resolve the central region directly, offering the first true image of the black hole's surrounding stars. Until then, astronomers rely on models built from faint shifts in spectral lines, tiny variations in light that describe a vast gravitational truth. Within those data lies the story of how a galaxy can remain motionless yet full of motion, unchanged yet alive with invisible dynamics. In its stillness, NGC 1277 encapsulates the paradox of time in astronomy. The stars that orbit its centre move at breathtaking speeds, yet the overall shape remains constant. The galaxy changes only in light, fading slowly as its population ages, while the structure, the balance of forces endures. The sphere of influence at its core acts not only as a boundary of gravity, but as a metaphor for permanence, a region where motion cannot alter the whole, where time's passage is felt only as repetition. Through that lens, the relic becomes more than an astronomical object. It is a symbol of stability in a universe defined by change, a frozen moment that continues to move, tracing the geometry of gravity across the eons. NGC 1277's central black hole stands as the defining engine around which all else orbits, but the questions it raises extend far beyond a single galaxy. Astronomers studying this compact relic have long sought to understand how such massive black holes shape the structure and fate of their hosts. In most galaxies, the growth of stars and the central engine follow a delicate balance. Gas flows inward to feed both processes, and the radiation released from accretion regulates further formation. Over billions of years, this feedback maintains the relationship observed across cosmic history between black hole mass and stellar velocity dispersion. NGC 1277 breaks that correlation, appearing to contain a black hole far too massive for its stellar mass. To grasp why scientists look backward to the early universe, when the first seeds of such objects formed in collapsing clouds of primordial gas, the relic's current state may be a fossil imprint of those formative years, when feedback, accretion and starburst activity intertwined in ways not yet fully understood. At the dawn of galaxy formation, dense regions of gas cooled and condensed under gravity, producing both stars and central black holes. These early systems, intensely active and compact, radiated enormous energy across ultraviolet and X-ray wavelengths. Observations of distant quasars show that some black holes reached billions of solar masses within the first billion years of cosmic time, implying growth rates near physical limits. NGC 1277 may have been one of these early sites of extreme accretion, where rapid gas inflow built a black hole even as it forged a stellar population. Once the gas was exhausted or expelled, the process halted, freezing the relationship between the two components. The result was a massive black hole surrounded by a compact metal-rich stellar system that has changed little since. In this view, the Relic galaxy is not an outlier but a survivor, a direct descendant of the primordial quasar era, long faded into quiescence. If this scenario is correct, NGC 1277 provides an unprecedented opportunity to study the end state of early coevolution between galaxies and their black holes. Unlike distant quasars obscured by dust and cosmic expansion, this relic is close enough for detailed observation. Its silent core, now devoid of accretion, retains the structural imprints of that violent beginning. The high stellar velocity dispersion, the rapid rotation, the compact size, and the overmassive central object all fit a pattern predicted by simulations of early dissipative collapse. During those initial phases, gas funneled into the center at extraordinary rates, fueling both starbursts and black hole growth. Feedback from radiation and winds then expelled the remaining gas, halting further expansion. The galaxy effectively completed its evolution in a fraction of cosmic time, achieving a mature configuration, while most others were still assembling. The absence of later mergers allowed it to retain this form, while the black hole deprived of fuel slipped into dormancy. The relic's quiescent state today hides the scale of energy, that once emerged from its centre. During its active phase, the black hole would have accreted matter at rates producing luminosities exceeding those of entire galaxies. Radiation pressure from the accretion disk would have heated surrounding gas to millions of degrees, creating outflows that pushed material outward in concentric shells. The same energy that now sleeps at the galaxy's core may once have carved cavities into the young interstellar medium, driving the feedback that quenched star formation. This self-limiting process in which a black hole regulates its host remains one of the central mechanisms thought to govern galaxy evolution. NGC 1277 provides an example of the end product, a system that experienced the process early completely and irreversibly. The absence of cold gas today is not simply an accident of environment, but a legacy of that feedback event frozen in time. The relationship between the relic's compactness and its central black hole also reveals how feedback influences structure. When radiation and winds expel gas, the stellar distribution can contract as the inner regions lose pressure support. The result is a galaxy that is smaller and denser than those that continue to accrete gas later. This mechanism may explain why the relic remains so concentrated compared with typical lenticulars. Its central black hole, by clearing out the gas reservoir, effectively locked the stellar system in place, preventing the formation of extended disks or halos. Over cosmic time, other galaxies underwent mergers that rebuilt their outskirts, but NGC 1277 remained untouched, preserving the compact configuration imposed by early feedback. In this sense, the galaxy's small size is not merely a remnant but an outcome, a structural scar left by its own central engine. Even in its current dormancy, the black hole continues to influence its surroundings through gravity alone. The velocities of stars near the core remain shaped by its pull, and the entire system's stability may depend on that central weight. Without it, the relic might have been more vulnerable to the cluster's tides or to internal dispersal. The black hole anchors the galaxy as surely as it once shaped its formation. Yet paradoxically, its presence also contributes to the mystery of apparent dark matter deficiency. If the central mass accounts for so much of the gravitational potential, little remains to explain beyond the luminous matter. The relic thus encapsulates a paradoxical balance, a galaxy whose stability and stillness arise from an engine that has long since stopped. Researchers continue to test whether NGC 1277 truly hosts one of the most massive black holes known, or whether modelling uncertainties have exaggerated its size. Each new dataset brings refinement but not closure. If the upper estimates hold true, the relic challenges our understanding of black hole growth limits, showing that extreme mass can arise even in compact systems. If the lower values prove correct, it still remains among the densest galaxies, relative to its size, confirming its status as an archetype of early quenching. In both cases, the lessons remain profound. Black holes need not evolve in step with their hosts, and some may reach maturity long before their galaxies do. From a broader perspective, the relic's central mass invites reflection on the long timescales of cosmic equilibrium. For more than 10 billion years, this black hole has remained dormant, absorbing only the occasional star or drifting gas cloud that ventures too close. Its event horizon is silent, yet the space around it remains distorted, shaping every orbit and every photon that passes nearby. The galaxy's light curves gently around this invisible anchor, and in that curvature lies the mark of deep time. What once was a blazing source of energy is now a perfect void, motionless, ageless, and absolute. The stars, unaware, continue their paths tracing ellipses carved by an absence that defines them. In the context of the Perseus cluster, this balance between presence and absence sets the relic apart. Other galaxies still exhibit faint signs of activity, weak jets, emission lines, or residual accretion. NGC 1277 emits nothing beyond the combined light of its stars. Its core is cold, its spectrum featureless, its radio signature nearly zero. It has become the quietest of survivors, a system where even the processes of decay unfold in equilibrium. The black hole's gravity ensures cohesion, its lack of radiation ensures silence. Together they form a state as close to timeless as anything in the observable universe. To study this galaxy is to peer into a paradox of creation and cessation. The same forces that once ignited its formation have also preserved its stillness. The black hole that grew through furious accretion now enforces eternal calm. In this duality lies the essence of NGC 1277, a relic that shows not how galaxies live, but how they stop. Around its core, the last light of an ancient burst still glows steady and unchanging, while deep within gravity continues its silent work, binding, shaping, and remembering an age when the universe was young and restless. NGC 1277 endures as a relic of coevolution halted a fossil galaxy whose development ceased while the universe around it continued to change. Its stillness contrasts sharply with the restless history of cosmic structures that grew through mergers and accretion. Where most galaxies evolved from small gas-rich systems into sprawling giants, this compact lenticular remained fixed in its early state. The evidence is written in every aspect of its structure, the uniformity of its ancient stars, the dominance of its central black hole, the absence of dark matter influence within observable bounds, and the complete lack of young populations or gaseous inflows. Each of these traits points to a moment when growth and transformation simply stopped. To describe NGC 1277 as frozen in time is more than metaphor. It reflects the physical and chemical equilibrium that has persisted for over 10 billion years, an equilibrium so complete that no new process appears capable of disturbing it. Understanding what it means for a galaxy to be frozen requires comparing the relic to its evolving peers. Across cosmic history, galaxies have changed shape and composition through collisions, star formation, and accretion. Gas infill feeds new generations of stars while mergers build extended halos and disks. These mechanisms constantly reset a galaxy's balance of mass and energy. In NGC 1277, all such activity has ceased. The relic's environment in the Perseus cluster prevents the reaccretion of gas by surrounding it with hot plasma that strips and sterilizes any incoming material. Without gas, there can be no new stars, no spiral arms, no future evolution. The result is an object permanently detached from the cycle of galactic growth, a survivor from an age when the first massive systems formed quickly and then were quenched by their own success. The fossil has remained in that state ever since an ancient model of what the universe's future galaxies may eventually become. This arrested evolution also reveals something about the interplay between internal and external forces. Within the relic, the equilibrium between the black hole and the stellar body has reached a state of long-term stability. The central gravity holds the stars tightly bound, while the absence of gas prevents further accretion or disturbance. Externally, the Perseus cluster acts as both cage and shield, a gravitational field so deep that it captures the relic yet protects it from slower, gas-rich mergers that would otherwise reignite evolution. The hot intracluster medium radiating in X-rays creates an environment hostile to star formation, but ideal for preservation. Within this balance, the relic has found its enduring shape, a compact core orbiting in a vast halo of heat and darkness, untouched by the dynamism that animates most galaxies. The cessation of evolution does not mean the absence of motion. Inside the galaxy, every star continues its orbit tracing paths established billions of years ago. The rotation measured in the outer disk and the chaotic dispersion near the center persist, as they always have, sustained by gravity but unaltered by time. These motions, stable and repetitive, constitute a kind of internal heartbeat, a mechanical rhythm in a structure where nothing new arises. The system's energy is conserved, its shape maintained through perfect balance. No gas clouds fall inward, no shocks ripple outward, no visible disturbances mark the passage of time. From an observational standpoint, NGC 1277 could have appeared nearly identical when Earth itself was forming. Its light has simply grown fainter and redder as its stars age a slow fading rather than an evolution. The black hole at its center too has entered a state of profound equilibrium. It neither feeds nor emits. Its surrounding space is quiet, devoid of accretion disks or relativistic jets, yet its gravity defines the structure of the entire galaxy, ensuring that stars remain bound and that the relic's compactness endures. The black hole's mass, whether several billion or more, dominates the inner gravitational potential, creating a stable well from which no material escapes. In that sense, it is not merely a remnant of past activity, but an active stabilizer of the present. Its influence extends invisibly through the motions of the surrounding stars, maintaining order without change. The relic is thus not static by neglect, but static by perfection, a system that achieved balance early and has sustained it ever since. From the standpoint of cosmic chronology, NGC 1277 offers a glimpse of the universe's direction over the coming trillions of years. Star formation across the cosmos is already declining as gas supplies diminish. Eventually all galaxies will run out of fuel, becoming collections of aging stars orbiting dormant black holes. The relic simply reached that stage first. Its stillness foreshadows the ultimate fate of galactic evolution, a cosmos where growth ends and only structure remains. In that distant future, the universe will resemble a vast collection of relics, each glowing faintly with the last light of long-lived stars. In this sense, NGC 1277 is not an anomaly, but an early example of a universal trend, a galaxy that embodies tomorrow's equilibrium today. The study of this frozen system also refines the understanding of feedback and self-regulation. In the early universe, intense bursts of star formation produced both radiation and stellar winds capable of heating or expelling gas. Black holes amplified this effect through jets and outflows that further dispersed material. The interplay between creation and destruction set a natural limit on galactic growth. NGC 1277 represents a case where this feedback loop was complete. The initial burst consumed and expelled all available gas before new inflows could arrive, ending formation in one final surge of light. What remains is a structure in which every atom of matter is accounted for, locked into stars, scattered into the cluster's medium, or bound forever to the central black hole. The absence of further transformation is thus the logical conclusion of its own internal physics. Even so, the relic's survival is remarkable. Over 10 billion years, gravitational tides, radiation and collisions have reshaped countless galaxies, but this one endures essentially untouched. Its small size helps the compact mass resist disruption, while the lack of extended features denies the cluster's tides a grip. The galaxy's motion through Perseus is measured but steady, following an orbit that never brings it close enough to the core for catastrophic stripping. It glides through a sea of hot gas and neighbouring systems, maintaining its distance, its density, and its silence. To observers, it appears as a tiny reddish ellipse set against the blue haze of the cluster, a simple form that belies its extraordinary history. The phrase "frozen in time" acquires literal meaning when seen in this context. In NGC 1277, every physical process that once drove change has been either exhausted or neutralized. Thermodynamics and gravity still operate, but they do so in a closed system that has reached its final balance. The relic does not evolve because there is no longer any mechanism by which evolution could occur. Even internal stellar deaths proceed quietly, their ejecta absorbed by the surrounding medium without consequence. The system's only change is the slow aging of light itself, as red giant stars cool and fade. To the cosmos, the galaxy has become a constant and unaltered witness to its own past. Yet its significance extends beyond stillness. The relic offers a benchmark against which models of cosmic evolution can be tested. It provides a reference for how early starbursts shaped chemical enrichment, how feedback quenched growth, and how compact galaxies might evolve in isolation. Every observation of NGC 1277 from metallicity to kinematics refines the story of how the first massive galaxies formed and why some stopped. Its continued existence affirms that the universe's diversity includes not only change, but preservation, not only expansion, but endurance. Through it, astronomers glimpse both origin and destiny, the explosive creativity of the young cosmos, and the serene permanence of its mature form. Seen in this light, NGC 1277 embodies cosmic memory itself. It carries within its stars the signature of the universe's most productive epoch, and within its silence the pattern of all that will follow. Around it, the Perseus cluster continues to glow and evolve, but the relic remains untouched, an ancient rhythm preserved inside a field of motion. The galaxy's light travelling across 200 million years of space reaches our telescopes as a message from a universe that has long since moved on. In that light we see both the history of creation and the promise of endurance, the shape of what the cosmos once was and what one day it will become again. NGC 1277 drifts in the heart of the Perseus cluster, silent and unchanged, while younger galaxies around it still trade matter and light. From a distance it appears as a dim amber lens set against a faint sea of X-ray glow, but within that simplicity lies one of the universe's most remarkable survivors. It is not just a galaxy, but a record preserving conditions from an age when cosmic structures first matured. Every orbit, every star, and every spectral line traces a chapter of that frozen history. As the cluster continues to evolve, its gas shifting, its galaxies colliding, the relic remains an unmoving reference point, an island of order within the tides of time. The question that now defines it is no longer how it formed, but how it has endured so perfectly, resisting entropy and collision in a universe built upon change. To answer that, astronomers look outward from the relic to the space that surrounds it. The Perseus cluster is an ecosystem of extremes, a vast gravitational basin filled with hot plasma dark matter and hundreds of orbiting galaxies. Its center glows in X-rays, energized by the activity of the supermassive black hole in NGC 1275. Shock fronts ripple through the cluster's gas like invisible waves, redistributing energy and stirring turbulence. In this environment, most galaxies are constantly altered, stripped of gas, stretched by tides, or merged into larger forms. Yet NGC 1277 remains compact and undisturbed. Its orbit carries it through the dense core, but not close enough to the violent central interactions. The same environment that erases the individuality of other systems preserves this one. The surrounding heat prevents new gas from cooling and falling, in locking the relic in quiescence. The cluster itself becomes the mechanism of its preservation, holding the fossil steady in its vast, hot equilibrium. Within this equilibrium, light becomes the only moving element. Photons from its ancient stars stream outward in all directions, carrying the spectral memory of conditions that have not changed for billions of years. Each one passes through the hot plasma of the cluster, bending slightly in gravitational wells, and scattering through magnetic fields before continuing into intergalactic space. By the time that light reaches Earth, it has travelled for hundreds of millions of years, a direct message from an era that predates the solar system. Through telescopes, that light reveals no trace of motion beyond the steady glow of old stars. There are no blue regions, no shadows of dust, no spiral arms to signal renewal. What observers see is the physical embodiment of time slowed almost to a stop, a system that has reached the final stage of stellar evolution, yet remains luminous enough to testify to its own persistence. The durability of such an object raises questions about the larger mechanisms of cosmic survival. In theory, even compact galaxies are vulnerable to erosion by the gravitational tides of their environment. Over billions of years, encounters with other cluster members could strip stars or alter orbits. The fact that NGC 1277 remains pristine suggests a deep equilibrium between internal density and external pressure. Its stars are so tightly bound that even the cluster's tides cannot dislodge them. The galaxy's compact size reduces its cross-section for encounters, and its stable orbit keeps it away from the most disruptive regions. It has achieved a perfect balance between isolation and connection, part of the cluster's dance but never entangled in its collisions. This same physics that confines its stars also confines its fate, ensuring that it will remain intact until long after its surroundings have changed beyond recognition. Inside the Relic, slow processes continue, but at a scale invisible to telescopes. Old stars evolve quietly into white dwarfs, releasing faint envelopes of gas that vanish into the cluster's medium. Some binary systems may end in supernovae, enriching the immediate environment with trace amounts of heavier elements, but those materials never accumulate into new clouds. Gravity immediately disperses them. The black hole at the center, though dormant, may occasionally capture a star or planetary remnant, producing brief flares of radiation that fade almost as soon as they appear. These events are rare, fleeting distortions in the otherwise continuous calm. On average, the Relic's energy output decreases with every passing million years, its color deepening as red giants cool and die. Yet the structure remains unaltered. Even decay unfolds in perfect symmetry. As scientists continue to refine observations of the Relic, its significance grows beyond the boundaries of the Perseus cluster. It provides a reference point for understanding the compact galaxies discovered at great distances, those seen in the deep fields of Hubble, and now the James Webb Space Telescope. Many of those distant systems resemble what NGC 1277 must have been in its youth, small, dense and red, already quiescent while the universe was still forming new stars at record rates. Until the discovery of the Perseus relic, such galaxies were thought to have vanished long ago through mergers and growth. The fact that one survives so near confirms that some avoided those paths. This single object bridges the gap between the ancient and the modern, showing that early cosmic structures did not all evolve into larger diffuse systems. Some, under the right conditions, simply stopped changing and endured. This endurance also transforms the relic into a natural laboratory for studying cosmic aging. By examining its spectrum, astronomers can trace the exact sequence of stellar lifetimes that unfolded during its early history. The ratios of different elements reveal not only how quickly the first stars formed, but how completely they enrich their surroundings. Every detail aligns with a picture of an early universe moving at extraordinary speed, a cosmos that built massive structures in the blink of its own geological time, and then slowed into stability. In NGC 1277, that stability has lasted for most of cosmic history. It is a map of how the universe moved from creation to maintenance, from chaos to calm. To imagine the Relic's future is to extend that calm forward across unthinkable time. Its remaining stars will fade into white dwarfs, and the galaxy's light will dwindle toward invisibility. The black hole will persist, slowly accreting what little mass remains nearby, until even that activity ceases. In trillions of years, when the Perseus cluster itself merges into the larger structures of the cosmic web, NGC 1277 may still exist, its compact core orbiting silently within whatever remains of the cluster's gravity. Eventually, when all starlight fades and the universe grows cold, the relic will become a dark mass of stellar remnants surrounding an eternal horizon. Its form will survive even as its brightness dies a fossil of both matter and motion. For now, however, the relic continues to shine faintly, a witness to cosmic history visible from across space. In its light, astronomers read the record of the early universe, the rush of formation, the surge of feedback, and the sudden quiet that followed. NGC 1277 is the result of all those processes reaching equilibrium, a galaxy that became complete before the universe itself had finished forming. Its existence tells us that creation and cessation are not opposites, but phases of the same cycle, that a galaxy can achieve permanence, not through change, but through stillness. Within the Perseus cluster's glowing heart, surrounded by movement and heat, it endures as the universe's quiet counterpoint, an object that embodies memory rather than motion. Its stars, born when time was young, continue to orbit in patterns that have not changed since their first revolution. To look at it is to glimpse the possibility that time itself can slow, that a structure can persist unchanged through cosmic ages, and that the universe in its vast complexity leaves behind islands of simplicity where history is not rewritten but preserved forever.